Hello and greetings from Berlin here in Germany for the presentation of our part in the BattleDIM 2020. My name is Ivo Daniel from the Smart Water Networks Group at Technische Universität Berlin, and together with a group from the Department of Civil Construction and Environmental Engineering at the North Carolina State University, we developed a two-stage approach titled a high-resolution pressure-driven method for leakage identification and localization in water distribution networks. Throughout this presentation, I will first briefly introduce you to our team, then I will elaborate on the methodology underlying to this work, followed by the presentation of the results, meaning the time and location of the leaks we found in the BattleDIM dataset, and also a very brief discussion.
So let's start with the introduction of our team. To tackle the challenge of the BattleDIM 2020, we decided to divide and conquer. The group from the Technische Universität Berlin focused their efforts primarily on the leakage identification part, whereas the group from the North Carolina State University focused their efforts primarily on the leakage localization part. Now, starting this off, I want to provide a general overview of the complete process with the following flowchart. In the first step, we obtain the time series of the raw data or the SCADA data from the pressure sensor readings in a water distribution network. This information serves as input for the leakage identification process and is used to build a linear regression model based on information from a normal state. The model is then applied to a state with a present leak and the reconstruction error is analyzed. From this analysis, we obtain information about the most affected pressure sensor, which is then passed to the leakage localization method. In a further step, the leak start time is determined, which is also passed as information to the localization method. Utilizing the information about the most affected sensor, the localization method provides in a first step the selection of several candidate pipes for the leak location. From these candidate pipes is then calculated by successive linear approximation the final location and magnitude of the leak. Now let's step into the details of each individual part. For the leakage identification process, we built a linear regression model based on the pressures of all available sensors. This model is calibrated in the first step for a time window where ideally no leaks are present. On the next two slides, I want to elaborate on how this linear model is possible and the derivation of the regression constants. The starting point to the regression is the Bernoulli principle as seen in equation 1, regarding energy levels at locations of sensor I and sensor J. As in this system, the pressure losses annotated for the respective nodes are calculated with respect to the supplying reservoir. From equation 1, isolating Pi and Pj yields equation 2. This can be transformed to the linear regression in equation 3, with the regression constant c reflecting the geodetic height difference between the nodes and the parameter m reflecting the relation of the respective pressure losses to nodes j and I. To analyze why this regression is possible, meaning why the expressions in equation 2 can be assumed constant, let's take a look at the term of the pressure loss divided by pressure for each node. In this term represented in equation 4, substituting the pressure at node I with the pressure loss relation of I and the reservoir yields the term on the right side. Now assuming constant reservoir pressure and constant daily average pressure losses, the expressions in equation 2 can be equally assumed constant. In the second step, the model is applied to the time frame with leaks and the model error is analyzed. The first part of the analysis obtains the most affected sensor by the respective leak. Assuming that a leak occurs in the vicinity of sensor I rather than all other sensors J, the reconstruction error of these regression models will result positive, as the increase in pressure loss at node I that are caused by the leak is greater than the increase at all other nodes J. The information of the most affected sensor is then passed on as input to the leakage localization method. In the final step, regarding the current evolutionary stage of the method, the change point is detected by visual inspection. This analysis was very straightforward for pipe breaks, as they caused abrupt change points and clear mean shifts in the signal, whereas gradually increasing transient leaks do not show an abrupt change point, but rather a trend change, which was a lot harder to pinpoint in time. The information of the leak start time is then also passed on to the localization method as input. The leakage localization method was initially developed and published in 2017 by the NC State team, as shown in the reference on the bottom right. The basis of this method is the formulation of a minimization problem, which describes the pressure difference that occurs due to a leak in a linear form and relating it to the leakage magnitudes. The pressure difference caused by the leak is calculated with the observed pressure from the n number of sensors in the network and the simulated pressures for the same locations under no leak conditions. Initially, leaks are inserted into the system at a number of m candidate pipes, and subsequently the leakage magnitudes are optimized using successive linear approximation to minimize the L1 error. The first step in this process is to select the m number of candidate pipes where the leak might have occurred. As a starting point to the selection, the most affected sensor from the previous step is taken, and the pressure difference that was caused by the leak is calculated for all pipes and then sorted descendingly by magnitude. The top 50 from this list are selected for further consideration, where the reduction to a number of 50 was derived after analyzing the dataset from 2018. Finally, for reasons of computational effort, from the initial set of 50 candidates, a reduced set of 10 to 15 pipes is sampled to obtain the final m number of candidate pipes. In a second step, the final leak location for all candidate pipes are calculated by successive linear approximation using a combination of linear programming and mixed integer linear programming. The solution vector will contain leak magnitudes greater than 0 for all pipes where a leak is located. In case of a single leak, the location is obtained as the algorithm returns the solution vector with a single element different from 0. Now let's move on to the results. For the dataset provided for this competition, we detected and localized a total of 18 leaks. The list on the left provides a complete overview of all leak start times and respective locations as they were identified by our method. Most of these leaks were located in the bigger DMA-A of the LTAR network. One was found in the lower DMA-B and another two in the upper DMA-C. The timeline chart illustrates that all leaks were fairly spread throughout the year. In this chart, the red lines annotate bursts or pipe breaks, whereas the blue lines annotate transients or progressing leaks. The colors are transferable to the map on the right, where the locations of each leak can be spotted. To illustrate the functionality of the method, we provide the example of the first leak found in 2019. In the leakage identification step, the produced reconstruction error signal from the model is shown here. During the first period, until January 15th at 11 p.m., the signal is steady around the 0 line. After that, a clear mean shift can be observed, indicating a pipe break. The figure also indicates that the apparent leak was fixed on February 1st at 9:55 a.m., as the signal indicates that the network returns to its previous state. The leak start time at January 15th, 11 p.m. and the most affected sensor node at node 506 are then passed to the localization method. Starting from this information, the candidate pipes are selected as shown in the map on the right, which represents the bottom left corner of the LTAR network. From the candidate pipes, the SLA algorithm then indicates that the leak has occurred in pipe 114, marked in blue on the map. Finally, I want to move on to point out some of the challenges that we faced when applying our method along this competition. Firstly, during the process of leakage identification, unsteady supply pressure conditions in DMA-C due to the pump and tank operation rendered the application of the regression method unsuitable. Instead, we needed to fall back to analyzing the mass balance, which was possible as in DMA-C 82 out of the 92 nodes were equipped with AMR technology. Also, as we mostly rely on visual detection of leakage start times, smooth transients caused real difficulties, as the transient to the leak state was rather smooth. On the side of the leakage localization, the model error inflicted in the EpiNet model is crucial to the accuracy of the algorithm, and the 10% error introduced for this competition already presented a challenge. Additionally, data for the seasonality of the demand was not available throughout the entire network, but was needed to calibrate the model. Therefore, the available data from DMA-C was extrapolated to adjust the demand of DMA-A and B. Better availability of the demand data would help in increasing the accuracy of the method. Lastly, the simulation optimization approach is computationally expensive, especially when needing to run for an entire year. This limits the level of detail in which the SLA algorithm can be applied. Specifically in this case, the number of candidate pipes needed to be sampled to achieve results in an acceptable amount of time.
So this presentation is coming to an end, and I want to use this opportunity to thank the organizers for the organization of this great battle and to thank my team for their great efforts. So thank you very much, and goodbye.